Okay, so who was it? Was it you, Missy? Yeah. Which number was it? 94. So 4.2, number 94. Yeah. Is this the diminishing returns one?
Yeah.
Okay. So I did post a video on Canvas for that. Probably I was a little rushed, so I probably didn't make the video as well as I could have, and it was a little bit longer than I wanted it to be, so sorry about that. Does anybody have the original function?
It's negative, or n of x equals negative 0.25 x to the fourth.
Okay.
Plus 13x to the third minus 180x squared plus 10,000. And it's 15 less than or equal to x, less than or equal to, I think that's 24.
24? Yeah. Okay. And then my guess is this is the sales function. X is the amount of dollars spent on advertising in thousands. Yeah. And then did they actually give you what the sales also in terms of thousands?
I think so.
Well, just real quick.
It says after spending X $1,000 on advertising as given by it.
Okay, so they're not really giving us the sales, and they're not giving us the units on sales. I'm just gonna assume that since X is in $1,000, the sales is probably also in thousands of dollars. That's what made more sense to me, because if you watch the video, I did a problem where they spent $8,000 on sales, and the value of the original function there was like, or it was actually not the value of the original function, but I think the value of the derivative was like 256, which to me would be weird, because that would say that every $1,000 you spend on advertising, you're only increasing your sales by $264, or something like that. So that seems like a low return for so much money spent on sales. Okay, so the point of diminishing returns is where the rate of change of the sales changes from increasing to decreasing. Okay, which ultimately is just saying the point of diminishing returns is just the inflection point. It's the place where the first derivative changes from positive to negative. Okay, so you can take a first derivative, which is going to be minus x cubed plus 39x squared minus 360x. Okay. And then you're going to have to take a second derivative. You'll get negative 3x squared plus 78x minus 360. I believe that is correct. Okay. So again, X is the amount of money spent in advertising in thousands. And the output of the function, my guess is that it's how many $1,000 you're getting in sales. Okay. So the point of diminishing returns, it's the place where the first derivative changes from positive to negative. So typically what you do is you figure out where the second derivative is 0 or undefined, and you make a sign chart, right? And then that sign chart is telling you where the first derivative is increasing or decreasing. Okay. I think we can factor this. The negative 3 can come out plus, let's see, 3 goes into 60 20 times. I think this is going to be 26x minus 120. And I don't know if that's going to factor or not.
Plus 120?
Plus, yeah, that should be a minus 2. Thank you. Is there anything that multiplies to 120 and adds to 26? 12 times 10. Let's see. 4 and 30. There we go. Is it 20 and 6? There we go. Okay, so this will factor as x minus 20, x minus 6. And then, like I said, essentially it's going to be the point of diminishing returns is where the rate of change changes from increasing to decreasing. That's what your sign chart for the second derivative is going to be. It tells you where the first derivative increases or decreases. So what you can do is you'll take your number line now. This is the sign chart for the second derivative. We only care about what's happening though between 15 and 24. So notice 1 0 of this 6 doesn't even matter. Okay, so the only critical number in this interval is going to be the 20. So 20, I'll say this, x equals 20 is the only partition number in the interval between 15 and 24. Okay. So what they're saying is that's the amount of available money they have to spend on advertising. They're always spending somewhere between $15,000 and $24,000 on advertising. And then you plug those values into this function, the output is going to be the amount of money in thousands that, it's going to be the amount of sales in thousands. Okay, so 20 is the only partition number. And then the only way for this to work, it better be plus, 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 and minus, minus, minus. Okay, because over here, wherever the second derivative is positive, that means the rate of change or the first derivative would increase. Okay, and wherever the second derivative is negative, that tells you where the derivative is decreasing. Okay, so if I plug something like a good test value to use in here would maybe be x equals 16. This is a negative term, so minus 16 minus 20 is negative, and then 16 minus 6 is positive. Negative times a positive is positive. Okay, so the second derivative is positive between 15 and 20. And then if you plug something like 22 in, the only thing that changes is that sign. That negative 3 is always negative, and then these two factors would be positive. So the second derivative would change to negative at 20. So x equals 20,000 is the point of diminishing returns. And my guess is they want you to find the rate of change at that value as well. Okay, that's also going to give you a maximum rate of change. Okay. And then n prime of 20 is the maximum rate of change in sales. Okay. So you might have to plug 20 into the derivative and give us the maximum rate of change in sales.
Wait, so with the diminishing returns, they don't want you to take that x value and then plug it into the original equation? They want...
No. Well, it depends on what they're asking. I don't have the question in front of me. The only thing I could really do is just go into the book real quick and take a look. You got it?
Yeah.
While you're doing that, I'll kind of show you what's happening graphically. This isn't going to be the exact graph. You could go into Desmos. I certainly went into Desmos on my video. So like maybe here's 15, here's 24. 20 is maybe right here. And the graph of the first derivative, I don't know what it's going to look like. It might look like something like this. So this is n prime of x. Right? So 20,000 in advertising is where the rate of change goes from increasing to decreasing. Okay? And then here's something you might see on the original graph, if I can do this right. And what this is really saying is that at the point of diminishing returns, it's really the place where the tangent line of the graph is the steepest. And then after that, your function starts decreasing. Okay, so your sales might still be increasing after the point of diminishing returns, but it's increasing at a slower and slower rate because the slopes of the tangent lines aren't as steep. Okay. So that's another way to interpret the point of diminishing returns. On the one hand, it's the place where a first derivative has the maximum value. It's where the maximum rate of change is. And then on the graph, if it's the maximum rate of change, it's the place where you have the steepest tangent line. It's also going to be an inflection point. Okay. And then, like I said, that's the point where the rate of change of sales is the highest. After that point, though, the sales are going to still be increasing, but they're increasing at a lower rate. So that's the point where you have the maximum rate of change in sales. And then what does it say?
It's just asking for the maximum rate of change, and then it asks us to graph n and n prime on
Okay.
the coordinate system.
Okay, so I kind of took care of it all.
Yeah.
And they also want the point of diminishing returns?
Mm-hmm.
Okay. Yeah, so since you do a sign chart for the second derivative, this is telling you that the first derivative goes from increasing to decreasing at 20. So 20,000 is the point of diminishing returns. It's just the point at which the rate of change in sales starts decreasing. Right? The rate of change in sales is increasing until you get to this point. That's where the maximum rate of change is. And then after that, the sales might still be going up, but the sales are increasing at a slower rate. So you're just finding the place where you have a maximum rate of change in sales. So yeah, you can use Desmos for this part. You can go and mess with the viewing window. You can change your viewing window from like 15 to 24 on the x-axis. And then the y-axis, you might have to play around, with what the values are until your graphs fall in there. So I'm okay if you use technology and then just draw a sketch of the graph on a paper. I guess you could also do all the graphing analysis if you wanted to by hand as well. But you should see the same pattern when you go graph them. On the first derivative, at the point of diminishing returns, the first derivative has a maximum, and that's on the original graph, that's where you'll see the steepest tangent line, because that's where the rate of change is the greatest. Okay, does that help? Okay. All right. So like I said, everybody have a copy of this handout for technically 4.4.
You missed it,
Oh gosh. Here you go. You want to slide those back and have everyone grab them. So again, make sure you fix it. It's not 4.3, it's 4.4, so that was my bad. Now, if I don't finish this again, I'm probably just going to make a video. Okay? So, it is absolutely crucial that I start section 4.5 on Monday. So if I don't get through this whole handout, what I'll do either tonight or tomorrow while I'm in the hotel up in Yakima for the conference, I will make a video for the other problems.
Wait, so are you going to be here tomorrow?
I will not be here tomorrow.
Oh.
Okay. If you go look at my schedule again that I posted on Canvas, you'll see that it says no class because I'm at a conference. And then there's still one more day we're not going to have class. So next week we'll have a full week, and the week after that, Monday is off for Memorial Day. In fact, none of us can get in. The college will be locked up that day. Okay, so again, if I don't finish this, I'm going to make a video. Now, it's still curve sketching techniques, so it's still going to be the same steps as in the previous section. Analyze the original function, the derivative, and the second derivative. It's just now we're going to look at functions that might have vertical and horizontal asymptotes. So that's the only extra piece here, right? Now we have rational functions, so now we have to figure out what the vertical and horizontal asymptotes are. Okay, so for example 1, we're going to look at f of x equals 2x over 1 minus x. We're going to state all pertinent information, and we're going to sketch a graph. Okay, so step 1. First of all, we need a domain. The domain is going to be the interval from minus infinity up until what value? So what can't I plug in for x? We can't plug in 1 because we'd be dividing by 0. Actually, let me write this a little smaller. Okay, so the domain is everything except positive 1. Then we still need to say what the intercepts are. And y'all can verify this, but the only x and y intercepts are just the origin. That's because when I plug in 0 for x, that's telling me what the y-intercept is. If you plug in 0 for x, you get 0. And the only time this fraction equals 0 is when the numerator equals 0, which is at x equals 0. Okay, so you find your x and y intercepts, you're going to find you only get the origin. And then you've got the vertical asymptote. And that's going to be x equals 1. So that's what makes the bottom 0, but not the top 0. Now, if I rewrite this in a certain way, can anybody tell me what the horizontal asymptote is?
-2.
It'll be y equals -2. That's because the power of x on the highest power of x on the numerator and denominator is the same, and the ratio of the leading coefficients is 2 divided by -1. Okay, so we've got a vertical asymptote at x equals 1 and a horizontal asymptote at y equals -2. Now, you might have to take the limit as you approach 1 from the left or right, because you need to know if you're going to infinity or minus infinity at the asymptote. You might be able to gather that information from the sign chart though. Right? If you're concave down and decreasing to the left of the asymptote, then that means you're going down to minus infinity. Okay, so I don't think you actually need to take the limits. I think you can use all the information about the concavity and the derivatives to know what happens close to the asymptote. Okay, and then step 2. This is to analyze the derivative. When I take the derivative, I'm going to keep it in this form, and we're going to have to use the quotient rule. And now the simplifying part is going to be a little bit more involved as well. So f prime of x is going to be the bottom function times the derivative of the top. So 1 minus x times 2 minus the top function times the derivative of the bottom, which is -1. And then we always divide by the bottom function squared. And let's see what this will simplify to. Actually, I don't think it's too bad, because you're going to get a minus 2x here, and that's just a plus 2x. So I think this is just 2 over 1 minus x squared. So we didn't have to actually factor anything there. You can just simplify the numerator. You can multiply things out, combine like terms. You'll just get positive 2. Does everyone see that? Because again, I'm getting a minus 2x plus 2x, that's 0, and then all that's left over is 2 times 1, which is 2. Okay. And then the derivative is 0 or undefined only at what value? Yeah, first of all, it's never equal to 0 because the numerator never equals 0. Okay. And then it's undefined when the denominator equals 0, which happens at positive 1. So there's no critical numbers, but the partition number is x equals 1. And again, that's because the derivative is never 0 and it's undefined at 1. Okay, and again, why would 1 not be a critical number? Or, yeah, right. You can only, a partition number is only a critical number if it's in the domain. Okay. Of the original function. Yep. So again, it's the reason we call it a partition number is it's still a number we put on the number line to find where the intervals of increase and decrease are. It's just there's not going to be any local max or mins because now we don't have any critical numbers. Okay, so you make the sign chart. So this is a sign chart for f prime. You can put 1 on it. And then, to be honest, hopefully everybody buys it that that's always positive. The numerator is 2, that's positive. The denominator is being squared. That always makes it positive. So on your sign chart, to the left of 1 we're increasing, and to the right of 1 we're increasing. So f is increasing on minus infinity to 1 and 1 to infinity. So again, we're just doing the same thing today. It's just the only difference is we have functions that might have horizontal and vertical asymptotes. That's all this section is adding in. So we're not really learning a whole lot of new stuff here. Okay, well that's step 2, right? There's no critical numbers. I guess I can write that up here. Since there's no critical numbers and there's no place where the derivative is going to change from positive to negative or vice versa at a critical number, f has no local extrema. You're not going to have any peaks or valleys. There won't be any local maxes. There won't be any local mins. So we analyzed the original function, found domain, intercepts, and asymptotes. We analyzed the first derivative, which gives us the intervals of increase and decrease and whether or not there's any extrema. And then what does the second derivative do for us? It tells us the intervals of concavity and possibly where the inflection points. The peaks and valleys are just the first derivative part. But yeah, the second derivative will tell us where it switches from curling up to curling down or something like that. So now we have to take a second derivative. I'm going to show everybody a little trick. You can use the quotient rule if you want to. I haven't shown anyone this trick yet because it hasn't really come up. But notice f prime of x could be rewritten as 2 times 1 minus x. If it's a positive 2 power in the bottom, you could write it as a negative 2 power up top. So that way you don't have to use the quotient rule. Now I haven't shown any of you this trick. It might have been in the textbook. You might have watched some video somewhere online, but there's nothing wrong with the quotient rule. It's just, I'm just going to skip it. I'm just going to use the general power rule. So now when I find the second derivative, what do I do with this negative 2 power?
Comes up front.
Comes out front to give us minus 4. The inside stays the same. You raise it to the next lowest power. And would I be done, or is there one thing you have to be careful about?
Multiplied by the inside.
And the derivative of the inside here will be negative 1. So, minus 4 minus 1 is positive 4. And in the bottom you'll have a 1 minus x cubed when I simplify. That's just a little trick if you don't want to use the quotient rule. Okay. And this equals 0 or is undefined. Again, at x equals 1. It'll never equal 0, but it'll be undefined when you try to plug 1 in the denominator. Now, this will still be a partition number for the second derivative. Is there going to be an inflection point at all? What do you think? Is there actually going to be a point on the graph at x equals 1 of the original function?
No, there's a vertical.
Yeah, there's a vertical asymptote there. So there's no inflection points. That's what I was getting at here, right? X equals 1 is a partition number for f double prime, but x equals 1 is not in the domain of f. So there are no inflection points. Even if the concavity changes at 1, which it will, there's not going to be actually any place on the graph where there's not going to be a point on the graph where the concavity changes. So I'm just adding in that little extra interpretation there. It's a partition number for f double prime. We'll still do our sign chart. We'll put 1 on the number line. The concavity might change there, but there's not actually a point on the graph where the concavity changes. Right? The concavity will change at this asymptote perhaps, but not at an actual point on the graph. I'm just making that distinction. Okay, so I think what I'll do is I'll erase this. I think I can sketch a graph right here. Okay. Although, what do I still need to do? I still need to do my sign chart for the second derivative. So you can make your number line, put your partition number of 1 on there. This time it will change sign because the numerator is always positive, but because the denominator has a cube this time, you're going to change signs at positive 1. What's a good test value to the left of 1 that would be easy to use? 0. So at x equals 0, you plug in 0, you're going to get 4 over 1. So you're concave up to the left of 1. And then you're going to be concave down. Well, if you pick, what happens if you plug in positive 2 to the second derivative? So 1 minus 2 cubed is negative. The numerator is still positive. So the second derivative is going to change signs at positive 1. So it's concave down on 1 to infinity. And then finally, here's our graph. I'll just go like 3 units in every direction. Okay, and you can sketch in your asymptotes. So at positive 1, there's the vertical asymptote. And then the horizontal asymptote is down here at minus 2. Okay. Now, as you move to the left, the function has to get close to this asymptote, and as you move to the right, the graph has to get close to the horizontal. And as you approach 1 from the left or right, the function either needs to go up to infinity or down to minus infinity. So let's see if we can figure this out. What point am I also missing? There's also a point on the graph. We found the x and y intercepts, and that only x and y intercepts were at the origin. Okay, so I think we can draw the graph to the left of the vertical asymptote. What is supposed to happen? The first derivative tells us it's increasing, and the second derivative says that it's concave up. And to approach the asymptotes, where did I put that marker? Here we go. You've got to start off close to this horizontal asymptote, increase through the origin, and approach the vertical asymptote from the left. Okay. You can also plot a couple extra points if you want, just by plugging some stuff into the original function. Like for instance, out of curiosity, what's going to happen at positive 2? Just to have a point to the right of the asymptote. 2 times 2, I'll just write it down here. F of 2 would be 4 over 1 minus 2, which I believe is going to be minus 4. So I actually didn't go down far enough. So here's another point on the graph. And then we have to pass through that point and make sure that we are concave down to the right of 1, but always increasing. So I think it has to look like this. Right, as you approach 1 from the left, you're going to go to minus infinity. And then we have to be concave down and increasing and approach that horizontal asymptote of negative 2. So there's a sketch of that graph. Okay. If you need to plot some extra points just to kind of know where the graph is, then I would recommend doing that. Like even for my sake here, I had to find an extra point to the right of the asymptote. So I just picked whatever. I just plugged in 2 and got -4. That tells me this is a point on the graph. And then I just made sure that I increased through that point, was concave down, and approached both my asymptotes. Okay. We'll probably have time for one more, and then like I said, I'll probably make a video today or tomorrow just for the last problem and get that posted. Okay, anybody have any questions just about the process? Yeah.
I just have one. I want to clarify on the second derivative.
Yeah.
You did 1 on the number line because it's a partition number, but I
Yep.
just want to clarify what the partition number is.
A partition number is just a value of x where the second derivative is 0 or undefined.
Pretty much you solve for x in that equation.
I didn't solve for x.
Or just like where it is 0 or
Yes.
Okay.
If there were some x's in the numerator, I'd have to set the numerator equal to 0.
Okay.
But since the numerator is 4, that'll never equal 0. And then this was a pretty simple equation. I didn't write it down, but I did technically set 1 minus x cubed equal to 0.
I just wanted to make sure that's.
Yep. But, just because 1 minus x is the only factor in the bottom, so it's only going to be 0 and x is 1. So when it's a simple equation, you're not really going to see me write it down and solve it. But theoretically, what you do to find your partition numbers is you set the numerator equal to 0 to figure out where it's 0, and you set the denominator equal to 0 to find where it's undefined.
Okay.
And then that'll give you partition numbers. And then you also have to ask if those partition numbers are in the domain. Like if 1 would have been in the domain, you would have had an inflection point actually on the graph. Okay. But this time there's no inflection point because the concavity is changing at an asymptote. And it's the same thing for the first derivative. I might have got rid of it now. But, we found the first derivative, and I don't think there was any critical numbers there either, so there's no local max or mins. But I did the same thing. I took the first derivative, which I think wasn't it, didn't we get 2 over 1 minus x squared? So I'd again set the numerator equal to 0, which never happens because the top is 2. And then if you set the bottom equal to 0, the only place that was equal to 0 was at 1. So I put that on the number line, and that tells me possibly where the derivative will change sign. Okay, good question though. But the steps, hopefully the steps are okay, right?
Oh yeah.
They're clear, right? Step 1 is,
clarify,
how much information can we get from the original function? Step 2, how much information can we get from the derivative? And that's just increasing, decreasing, and if there's any extrema. And then you'd find all the information you can from the second derivative, which is the concavity and possibly where there's inflection points. Okay. It's a lot. I remember when I first learned this, I was kind of surprised at how long these problems take. They're just by their nature time consuming. I do little things on the tests, like I might just give you a lot of this information and ask you to sketch a graph. One question might just be, what are the intervals of concavity? So on the test, you're not going to have to do a full analysis. Like I'll break it up into little pieces that you can do. Because, right, this would be tough to do these on a test, right? It would take you a long time to get through one of these. Okay, so a lot of times I either provide you with this important, you'll see it when you do the homework. I assigned a homework problem from this section. One of them is just telling you, actually they don't tell you what the vertical and horizontal asymptotes are exactly, they give you the limits. And you have to use the limit definition. Like, they'll tell you the limit as x goes to infinity of the function's -2. But that's really telling you that's the horizontal asymptote. They might tell you the limit as x approaches 1 from the left is infinity, which is telling you that x equals 1 is a vertical asymptote. Okay, so I might not tell you what the asymptotes are, but I will give you the information to find the asymptotes. You'll see it on the homework. I have a problem where I essentially give you the asymptotes using the limits, the domains given, and then you'll have a couple sign charts that tell you where it's increasing, decreasing. So you're going to most likely have one of those on the test. Okay. Because like I said, it's too time consuming on a test to start with a function and get all this information on your own. So I have to do things to shorten up the questions so that you have time to do other questions. Okay. So example 2, we're going to do the same thing. We're going to analyze a different type of function. So our function this time is going to be f of x equals x e to the minus 0.5x. I'm going to find all the pertinent information, namely the information on the function, its derivative, and the second derivative. Okay, and then we'll go ahead and sketch a graph. So step 1, I think the domain should be pretty easy right away. The function x is a linear function, domain all real numbers. Is there any restrictions on what you can plug in the exponential? No division by 0 or negative square roots. So this function is going to have domain all real numbers. Yeah?
So if there wasn't the x out in front and it was just e to the 0.5x, would that be only greater than 0?
Nope, it'd still be all real numbers.
Okay.
Exponential functions are defined everywhere.
Okay.
It's only logarithmic functions that have restrictions on the domain, but we're not worrying about log functions.
Mm-hmm.
Okay. So yeah, there's no division by 0, there's no natural logs of negatives or square roots of negatives. You can plug anything in you want, so it's all reals.
Okay.
Okay, and then what else do we need? We need the asymptotes and the intercepts. Okay. So the intercepts, I think again this is just going to be like the previous one. If you plug in 0 for x, you're going to get 0. So the y-intercept is 0. But if you set it equal to 0, the first factor can never be equal to 0, so only x can equal 0. So I think it's just like before, the x and y-intercept is just 0, 0. Whether you plug in 0 or set it equal to 0, your x or y coordinate's going to end up being 0. All right, now for asymptotes. This might be a spot where I shouldn't have skipped L'Hopital's rule. So there's no horizontal asymptotes, I can tell you that right away. Right? Because we're not dividing by anything. There's never, and plus the domain's all real numbers. So there can't possibly be a horizontal asymptote or vertical asymptote. Okay. And then let's see here. There will be a horizontal asymptote. And the only way to get it is to analyze these two limits. It's not just a rational function, right? If it's a rational function, we have the tricks. We have the shortcuts for what the asymptotes are. This time we're going to have to take these limits. And I think we have to do it with a table. On the test, I would never... I'd probably give you a rational function and have you find horizontal asymptotes that way. Okay. So here I'm more interested on like the first derivative and second derivative analysis. And unfortunately, I have to make a table for these limits. So some of you are going to get out your calculator. Half the room's going to do the positive limit, the other half's going to do the other one. So to find these limits, I need to make a table. So I have x and x e to the negative 0.5x. And for the limit as x goes to infinity, we're going to do 10, 100, 1,000, maybe 10,000. So if somebody could start plugging these values into that function. And then for the other limit, I'm going to have to make a table where the values are getting more and more negative. Okay. This is what L'Hopital's rule was for in the previous section. It gives you a shortcut for how to do limits at infinity, but like I said, for the most part, we don't need it, so I guess I can help with the negative ones. Well, that's getting big quick. I think that one's pretty easy to see is going to be minus infinity. You start plugging more and more negative numbers in, it just starts getting ridiculously large. My guess is that this limit's going to be 0. Anybody want to share? Anybody get something for 10, 100, 1,000?
Just gets really, really, really small.
Like really fast? Like what'd you get when you plugged in 10?
0.067.
And yeah, this one might already be giant already. Yeah. You already get 1.9 times 10 to the minus 20, which means you're moving this decimal 20 to the left. These are just going to keep getting, your calculator is probably even going to tell you that at 1,000 it's just 0, I bet. Yeah. It's not identically equal to 0, but your calculator rounds everything to 10 decimal places at most. Okay, so this limit is 0. That implies the horizontal asymptote is y equals 0. And you only approach it from the right. Okay, so that's like the right-in behavior. As x gets larger, the graph is going to get close to the x-axis. As x gets more and more negative, the function's going to go down forever. Okay. Remember, infinite limits are the in behavior. Okay, so that was a little bit more work than I wanted to do, but like I said, I'm not going to make you do this on the test. If I was going to ask you a question on the test where you needed the asymptotes, I would certainly give you a rational function where you can use the shortcut. Okay. All right. So we had to do the limits. What did we call that before? There was algebraic, graphical, algebraic, and then forget what the other one was. Numerical. It's doing a limit numerically. Okay. And then that's step 1, so no vertical asymptote. The only intercept is the origin. Domain's all real numbers. There's a horizontal asymptote of y equals 0, but you only approach that on the right side as x gets large. On the left, as x gets more and more negative, the function's just going to keep decreasing. Okay. And then we can go to step 2. Oh, we do not have time. I got to get through this. So we got to do the first derivative f prime of x. So for this, I think we have to use what derivative rule? We got to use the product rule, right? This is the first function. That's the second function. So I have my first function x times the derivative, which is just the same thing times the derivative of the exponent. So the derivative of e to the minus 0.5x is minus 0.5 e to the minus 0.5x. And it's going to be plus the second function times the derivative of the first, which is this positive 1. I think this is pretty easy to factor. Both terms have an e to the minus 0.5x in them, and then it just becomes 1 minus 0.5x. So I switched the order, right? It's minus 0.5x plus 1. And this is never undefined, but this equals 0 when x equals 2. Now, I didn't show the work here, but let me at least explain what I did. When you have two factors that are equal to 0, I set this first factor equal to 0, but it's an exponential. It never crosses the x-axis. So I only have to know when this factor equals 0. 2 times 0.5 is 1, so 1 minus 1 would be 0, and x is 2. Okay. And that's actually a critical number this time. Okay. And why is it a critical number? Because it's a partition number that's in the domain, right? The domain is all real numbers. So any partition number is automatically a critical number. So this is also, I guess, what else? Not also, but I'll say it's the only critical number. Okay, so now we can make our sign chart for the derivative. We can put 1 on it. Now, I have the derivative in a factored form already. If I pick something to the left of 1, like x equals 0, this factor is always positive. And when you plug 0 into this factor, you also get positive 1. So the derivative is positive to the left of 1, but if I plug something, oh, not 1. What did I do? Yeah, that should be a